Hi, my name is Rifa Ahmed Maisha, and today I will present my project titled Parallel Implementation and Optimization of 2D Image Transformations using CUDA. So in this project, I implemented several common image transformations on both CPU and GPU. Then I compared their performance and explored different CUDA optimization techniques. So here is the outline of my presentation. First, I will describe the objective of the project and the image transformation functions I implemented. Then I will explain the CPU baseline and knife CUDA implementations. After that, I will compare the CPU and GPU performance, talk about the arithmetic intensity, and explain why I selected rotation for further optimizations. And finally, I will discuss the optimization techniques such as register tiling, shared memory tiling, and textured memory, and the overall conclusion. So the main objective of this project is to implement a 2D image transformations using CUDA and compare the serial CPU execution with the parallel GPU execution. The transformations I used in this project is crop, resize, flip, grayscale, and rotation. The images on the left are the output generated by this operation. The another objective of this project is to investigate whether the CUDA implementation could be further optimized from the initial knife version. Here we see the basic mathematical operations used for each transformation. For cropping, I simply shift the source coordinate by the selected crop location. For resizing, I used nearest neighbor interpolation. The source coordinate is calculated by scaling the output coordinate according to the ratio between the original and new image dimension. For horizontal flipping, the x coordinate is reversed while the y coordinate remains same. And for vertical flipping, the y coordinate is reversed. For grayscale conversion, I calculated the weighted combination of red, green, and blue channels. The rotation is more complicated. For each output pixel, I performed inverse mapping to calculate which source pixel should be read. It involves sine and cosine calculations for the angle and translation around the center of the image. In this slide, I showed the serial CPU implementation as the baseline. The CPU version uses nested loops and processes the pixel one by one. Then I implemented the same transformation in CUDA. In the knife CUDA version, one CUDA thread processes one output pixel, and each thread calculates its own x and y coordinate using block index, block dimension, and thread index. The thread then directly reads from and writes to the global memory. So the main difference is that the CPU processes pixels sequentially while the GPU can process a very large number of pixels in parallel. So the graph here compares the CPU execution time and GPU kernel time for each transformation. The vertical axis is shown on a logarithmic scale because the difference between the CPU and GPU kernel time is very large. For all transformations, the GPU kernel time is significantly smaller than the CPU kernel time. If we see the speed up kernel, the GPU is 1019 times faster than the CPU. But however, the kernel only speed up doesn't include the data transfer. When host to device and device to host transfers are included, we get the total speed up, and it is for this GPU is 27.27% faster than CPU. So the CUDA still provides a very large performance improvement even when the memory transfer overhead is included. I also tested different image sizes to understand how the implementation scaled. As the image dimension increases, the CPU execution time increases very quickly. It's because for increasing the size of the image, the CPU has to process many more pixels sequentially. but for GPU kernel time, it increases much more slowly because the work is distributed among many CUDA threads parallelly. This means the GPU acceleration becomes more beneficial for larger images. I also tested CUDA blocks, different CUDA blocks such as 8x8, 16x16 and 32x32, and from my measurement 16x16 produced the lowest total kernel time. So I used 16x16 for the following experiments. Now we see arithmetic intensity. Arithmetic intensity is approximately the number of floating point operations performed divided by the number of bytes transferred from memory. If the arithmetic intensity is high, it means it's in the computation bound, and if the arithmetic operation is low, it means it is in the memory bound. For crop, resize and flip, there are almost no floating point arithmetic operations compared with the amount of memory being read and written. Therefore, the arithmetic operation is 0 and it is in the memory bound. The grayscale requires 3 multiplications and 2 addition, so the arithmetic intensity becomes 0.83 flops per byte. It is still very low, that's why it's mostly memory bound. Rotation performs more calculations, including multiplications, addition, sine and cosine related coordinate calculations, and the arithmetic intensity is 1.67 floats per byte. It is higher than other operations, but it is still very low. That's why we can see it's also mostly in memory bound. After analyzing the execution times, I focused on the optimization on rotation because rotation has the highest GPU kernel execution time among all the operations. There are two main reasons for this. First, rotation requires more arithmetic operations per pixels because we need to coordinate translation and inverse rotation calculations. Second, rotation has an irregular memory access pattern, which means neighboring output pixels may not be the consecutive pixels from the source image. In my naive implementation, each individual rotation accounted for 30% of the total kernel time. That's why I tested 3 optimization methods: register tiling, shared memory tiling, and texture memory on rotation. So the first optimization I tested was register tiling. In the naive implementation, one CUDA thread process one output pixels. For example, thread 0 process pixel 0 and thread 1 process pixel 1. But in register tiling version, one thread process 2 adjacent output pixels. For example, thread 0 process pixel 0 and 1 and thread 1 process pixel 2 and 3. The goal was to reuse the same thread for 2 pixels and reduce the total number of active logical threads. The code shown here calculates a base x coordinate, xy coordinate, and then uses a loop to process 2 pixels. However, the result was actually slower than the naive implementations. This shows that an optimization technique doesn't automatically improve performance. In this case, assigning more work to each thread didn't provide enough benefit to overcome the additional overhead. The second optimization was shared memory tiling. The idea here is to reduce repeated access of global memory. Threads within the same block first cooperate to load a small region of the source image into shared memory. Because shared memory is much faster than global memory, the threads can then access pixel from the shared tile. After loading the tile, I used a sync threads to make sure all threads have finished loading the data before it is used. The goal was to reduce global memory traffic. However, the result was again slower than the naive implementation. Shared memory tiling was slightly faster than the register tiling, but still slower than the naive implementation. The likely reason is that loading the tile, calculating required source region, and synchronizing the threads introduce additional overhead. In this problem, the reuse of source pixels wasn't large enough to compensate for that overhead. The third optimization was texture memory. Texture memory provides a read-only CUDA memory path with hardware-managed cache. It is particularly useful for 2D image processing and when the neighboring threads access nearby source pixels, but the pixels are not in a consecutive order. For example, if we see here, we need to access FGJK, which is not in a, which they are nearby and neighboring pixels, but they are not in a consecutive order. For this, texture cache is used. Rotation does exactly this type of access patterns. So instead of manually loading a source tile into shared memory, I created a CUDA texture object and used text2D to read the source pixels. The texture cache automatically tries to exploit spatial locality. As shown in the graph, texture memory was the only tested optimization that improved performance compared with the naive implementations. The total rotation time decreased from approximately 0.579 millisecond to 0.552 milliseconds, which corresponds to a 4.6% reduction in rotation time. Now for the conclusion, we can see that CUDA code significantly reduced the execution time compared with the CPU execution, and GPU perform as the image size increases, GPU performance increases, and most transformation I used here are memory bound because they have little float point operations. Rotation has the most operations and most time expensive. That's why I chose it for further optimizations, and among all the optimization, texture memory gave the best rotation performance and it reduces the rotation time by 4.6%.